Hello, everyone. Thank you for sticking around for the last session of this conference. And thank you again to Matt and the entire Q2B team for bringing the community together. I must tell you that I feel very small on this stage next to these quantum giants, but it is what it is. Earlier, Scott, you mentioned that you are satisfied or pleased with the progress of quantum computing because you had fairly low expectations. So I wanted to ask you, John, perhaps, how do you feel about it?
Well, one would always like to see faster progress, but I think we've learned a lot of things in the last couple of years, and I would like to see acceleration of the progress, and there's a possibility that'll happen in the next few years.
And when you think about progress, there's scientific progress and there's engineering progress. Do you think we are pretty far along with the science and now it's mostly engineering, or how do you see that?
I think that there's a lot of science to be done. Now, science by its nature is unpredictable, right? What direction that it goes in. I mean, that MIP star, that quantum interactive proof systems with entangled provers would have the power to solve the halting problem. I don't think that was on just about anyone's bingo card 20 years ago, right? If by scientific progress people mean specifically new algorithms to solve industrially relevant problems, well then, we'll have to get very lucky, right? That those might or might not be out there. We can and should search for them. But scientific progress in general, I think there's absolutely a lot of progress, and connections between quantum computing and ADS-CFT, quantum gravity, condensed matter physics. I think that we're seeing all of that, and I think that's very healthy, and I'm excited about it.
I think the number one thing that would make a difference both scientifically and for the industry would be the discovery of new applications. And even if they're scientific applications, at least to begin with, I think that helps to propel the field forward and will lead to commercially relevant applications down the road. And I also think we have to continue exploring on the hardware side. There may be modalities we're not even thinking of today, which will turn out to have big advantages over the current ones. And I think it's an instructive lesson that, if you look back 5 years or so and you were thinking about the main hardware modalities that were the most promising, you probably would not have said Rydberg atoms and optical tweezers, and here we are. So it's a good thing that people were pushing that science forward.
A lot of the funding comes from governments these days. And if you were advising governments where to invest in algorithms and applications and hardware and education, maybe you are advising some governments today, what would you say?
I would like more for undirected basic research. There was this National Quantum Initiative Act that was passed in the US in 2018, I think. It was written by then Senator Kamala Harris, signed by then President Trump. But I visited Senator Harris's office when they were writing this bill. I talked to them. There was $1 billion of new funding for quantum research. My worry is if sort of all of that gets captured by sort of people who sort of have big consortia with like a very specific plan, and this is what we're going to do, and they're very good at sort of capturing large amounts of money, and meanwhile much smaller amounts of money that could go to people who have to support students who have a totally new idea that will change everything. That's somehow much harder. That's somehow not available. And so I would try to make sure that the latter is available, especially because it tends to be much cheaper.
I think the government is in a position, at least theoretically, to have a longer-term vision than most companies do. And I agree with Scott that government funding, which creates a healthy research ecosystem can lead to breakthroughs, which will have a big impact on industry down the road. But the government is also a very important customer for the companies. And so when it makes sense, if the government makes investments that benefit the companies and help them to develop their technology more rapidly, that can also be beneficial.
Q2B is the last, at least commercial conference of the year, thankfully. If you look back, what do you think was the most significant development in 24? And if you're here on the stage with us next year, this time, what would you like to see?
I mean, in terms of experimental developments, I would nominate, the progress that there has been in demonstrating quantum error correction, including what we heard about at this conference, the Google's use of the surface code to protect the logical qubit for longer and longer times as the code distance gets bigger. There have also been neat demonstrations of quantum error correction in trapped ions, in neutral atoms. I believe that was also this year. I believe that was also within the cutoff time. Theoretically, as I said in my talk, I'm a big fan of this DQI and in general of the sort of algorithmic advances that seem to be coming out of that Yamakawa-Gendre breakthrough. What I'd like to see next year, I mean, let's see a logical qubit with 10 to the -6 error. Why not, right? As long as we're making a wish list. Let's see quantum algorithms for hard optimization problems without algebraic structure, that get better approximation ratios. I mean, I have my own wish list of questions in quantum complexity theory that I'd like settled, QMA versus QCMA and so forth. But maybe that's a little less interesting to company founders and investors.
Well, Scott gave some good answers, and which I agree with. Just to add to that, in addition to the hardware progress, I think there's been a lot of progress on the theoretical side relating to quantum error correction and fault tolerance. Of course, we've seen a lot of recently discovered codes that are more efficient than the surface code, which at least down the road may have big benefits over the surface code that we know and love. And some of the progress this year has been in understanding better how to make use of those codes for fault-tolerant processing and doing universal gates with an advantage over other methods. Another arena to keep an eye on is the algorithms for classical simulation of quantum systems, and I think there's been a lot of progress there as well, in particular in the case of the types of simulations that physicists are typically interested in, where you prepare an initial state, let it evolve in some manner, and then measure local observables. It's been noticed that the classical algorithms can be improved a lot, and we always have to stay aware of that when we're looking for opportunities for quantum advantage.
Maybe I'll ask you first, John. In this area of tense geopolitics, how do we ensure continued academic collaboration across borders? Do the guardrails need to change, in your opinion?
You're talking about international cooperation. Well, it's a concern. Because there is a national security component of how quantum computing potentially can change things, there's understandable concern about the technology being used responsibly. But I would much prefer that US government policy emphasize accelerating progress in the U.S. Rather than, trying to stunt progress elsewhere, I think that will, in the end, be, better for the world and better for the quantum community. And one obvious area of concern for both the universities and national labs and companies is immigration. And we would like the brightest people in the world to continue to come to the United States to study and work. And I don't want to see that opportunity diminished. I think that would be very bad for the U.S. and for the quantum enterprise more broadly.
I mean, I had a spectacular undergrad who I knew in Beijing, who I wanted to recruit to UT Austin as a grad student, and he was not able to get a visa to come, apparently because he mentioned the word quantum on his visa application. And I blogged about it, and someone from the White House said, this shouldn't be happening, let me look into this. And then it turned out that he couldn't do anything about it, okay? So even the White House can't fix this, apparently. And that was in the current administration, right? So I've heard that I can't confirm this, but that it's become common knowledge in some parts of the world that if you want to get a visa to study in the U.S., you could say, well, I'm going to study 2 to the n dimensional Hilbert spaces, and unitary operators on them. But just whatever you do, don't mention the word quantum. I think that that's a self-defeating policy. I have said as much when I've met with Congress people, policymakers, that actually if we just gave all of these students visas, a large fraction of them would stay here if they could. And that's a huge competitive advantage that this country has. So yeah, that is something that I feel strongly about. Now, I happen to live in Texas, and there, things, just this week, we learned that the rules have been tightened so that we can no longer use university money to travel to China, for example. And, I think, not being a fan at all of the Chinese Communist Party, I don't see what such policies buy us. They seem self-defeating to me.
Scott, I think that during a sabbatical you did some work on ethics for OpenAI. Are you
safety, alignment.
Safety.
Yes.
Are you worried about safety and ethics for quantum?
Somewhat. I mean, look, there's an ethical dimension to anything that humans do, right? Now, with AI, there's a very special issue, right? Because we're going to be creating this new kind of intelligent entity and releasing it into the world, and it's going to be pursuing goals autonomously, and we don't really understand yet how to align the goals of these entities with the things that humanity values, right? And I think that's a huge question. The ethical questions in quantum computing I see as mostly just continuous with the ethical questions in classical computing, right? They're the sorts of things that we've dealt with for a long time, right? There are always ethical issues around cryptography and cryptanalysis, and of course those will come up. The good thing about a quantum computer as compared to a nuclear weapon, let's say, is it's not going to directly, kill anybody unless the dilution refrigerator tips over onto them or something like that. Okay, but there are always ethical issues in any kind of computing, I would say.
John, your thoughts?
Well, I agree with Scott that quantum computing doesn't pose the same kind of existential risk to human civilization that AI does. I think we will be best served if the benefits of quantum computing are widely shared in the future and not in the hands of just a handful of companies or a handful of countries.
To what extent do you guys keep up with the horse race in hardware? I mean, when Willow with 105 qubits or Heron with 127 qubits, do you care, or do you focus on a particular attribute of that processor?
I mean, I certainly care, but I don't pay as much attention as I probably should. Like, mostly I get push notifications, right? Like, either, a company will say, we are going to make this announcement next week, and we want to brief you on it. So, okay, fine. I talk to them, or, I visit someplace, and, they say, we want to give you a tour of our lab, talk about it, or something just appears in the news, and then because of my blog, I start getting emails about it. Like, why haven't you blogged about this? Why haven't you responded to this? Or people on Twitter are saying, well, there's no post on Aaronson's blog about this, so who can possibly know what to think, right? Which is flattering in a way, but it's also like, come on, right? So these are the kinds of events that that cause me to try to stay updated on what is happening. And it's like I don't have sort of ground level, base level knowledge about any of the proposals, but it's sort of like in theoretical computer science, we think about like a weak verifier who's like has these super powerful but competing provers who can be pit against each other, right? Like, I can listen to the trapped ion people tell me for hours why superconducting will never scale, and then the superconducting people tell me for hours why trapped ion will never scale, and then I can try to somehow triangulate what they're telling me.
Well, I'm always interested in the hardware progress. Sometimes the things that catch my attention are not the same things that make the headlines. For example, in the case of the recent Google experiments on quantum error correction, I was quite impressed by the experiments they did with the repetition code, not a quantum code that can correct any type of error that affects a qubit, but it was quite interesting that they could perform continuous syndrome measurement in the repetition code for hours with good stability of the device. And I was particularly interested in the achievement that with gap engineering, they were able to strongly suppress the burst error events, which had set an error floor in their experiments a year earlier.
And just before this talk, Google gave a very nice talk about explaining the experiment. So when the videos are available, you guys should all watch it. Getting back to the topic of government, do you feel that the government should fund a Manhattan project to build, a quantum supercomputer?
Well, I mean, the Manhattan Project has, specific connotations, including secrecy, right? I like to say that if someone started a Manhattan Project today to, build a quantum computer in secret, I think, within 5 minutes it would be on Twitter or X, like, hashtag what is going on in, Los Alamos or whatever, right? So, very, very, very hard to have a giant secret project anymore in this hyper-connected world, especially because, we would all notice that, lots of people, have been sucked into a black hole. So, but as for whether there should be like one giant effort to, I mean, right now the model of companies doing this seems to be working, right? Companies are, whether we think that it's a wise decision or an unwise decision on their part, the fact is that big companies and venture-backed startups are making these big investments. And so, let's see that play out. Let's see how far it goes.
Well, I presume that increased government investment could make some things happen faster. But I'd be pretty reluctant to focus the resources on a particular hardware modality at this stage. I really think we have to recognize we're still at a pretty early stage, and there could be a lot of surprises in the hardware arena that basic research will unveil. I don't know if we're ready to make that kind of focused effort.
It surprises me. I mean, as I mentioned to you before, I would have imagined that by the time things had reached this point, like we would have had a clear winner among the hardware paradigms. And it puzzles me that we don't.
Speaking of modalities, how do you feel about annealing? I mean, is that true quantum? Is that going away, you think?
Well, one of the things which was a bit of a surprise to me in the past year or so was experiments done on the D-Wave machine, which were not really annealing, but which I thought were scientifically interesting, because they have a unique device in that, you know, there are 5,000 qubits, but they're very poor quality qubits, and so there have always been questions about whether they're really seeing quantum effects when they operate the device at scale. But what they've recently done is they've been able to, you know, do very, very rapid quenches in that device, you know, ramp the artificial magnetic field very rapidly. And because that time scale is so short, you can argue that the effects of decoherence are not so severe. And they've seen evidence of universal behavior in quantum phase transitions, and which I think are scientifically intriguing. So that's not a direct answer to your question, but I think that hardware, which was originally intended to be used as an annealer to solve optimization problems, could turn out to have some scientific applications which are rather different.
I mean, I have always been much more excited about universal fault-tolerant quantum computation, you know, than I've been about things like annealing, right? That hasn't changed, you know, and I think that's true even if your eventual goal is to run, you know, say the adiabatic algorithm, right? I would rather see the adiabatic algorithm itself run on a universal fault-tolerant device than run on these very specialized annealing devices, right? And, you know, the reason for that is, you know, I want to separate the issues, right? Like with an annealing device, you never quite know, like you know, if I'm not seeing a speed up over classical, is that because of the temperature of the system, you know, because of the limitations of the hardware, or is that because of the inherent limitations of, you know, quantum adiabatic optimization itself? You know, with a universal device, at least we would know that it was the latter.
As a theorist, I think there are intriguing questions about annealers. We know that if we had an annealer which was not prone to error at all, it actually could be operated as a universal device. But the issue of how to make that fault tolerant is a rather different question than how do we make you know, universal quantum circuits fault tolerant. And I've sometimes felt that is a question which has received insufficient attention.
One of the questions from the audience deals with the intersection between academia and industry, which in this early stage is very tight. And the question is, if you had discovered an algorithm with exponential advantage for finance, would you publish it or would you go to a trading company?
I mean, if you're asking me to predict what I would do, I would publish it, and then maybe later I would kick myself. If you're asking what I should do, that's you know what my family would prefer that I do. That's a different question.
I'd publish it.
You'd publish. Very good. They all want the algorithm. What they would do with it is a different story, right? Yeah, related to exponential, right? So the question is, there was a paper earlier this year. How significant is it? The paper was exponential quantum speedup in simulating coupled classical oscillators.
So this was this paper that showed like a BQP complete problem. If I remember correctly, which paper you're talking about, this was like, they show that you can have like an exponentially large system of coupled oscillators, and you can formulate a problem about it, and they show that that problem is complete for BQP. So in other words, it's like another way of expressing quantum computation itself. I thought that that was a nice result, but whenever you say a BQP completeness result like that, it's often hard to interpret it as sort of an independent quantum speedup, because what you're saying is just that this problem contains all of quantum computation, which means, okay, if I now want to actually see an exponential speedup for this problem, then I'm probably using my quantum computer, then I'm probably looking at like a special case of the problem where I engineer my oscillators in order to encode Shor's algorithm, or encode some other situation where I already knew that there was an exponential speedup, right? So I think these are very nice theoretical results, but their practical significance is harder to say until you can show why would we see an advantage for naturally occurring instances of the problem.
Yeah, go ahead.
Please.
No, I would only say I'm in accord with Scott's answer.
Okay.
So when you see the Wall Street Journal or New York Times publish, XYZ company is going to break Bitcoin or has done this, I mean, do you go, oh my God, or is it yay? I mean, how do you feel about the hype in quantum computing?
I mean, I might read the article at some point and say, do I think this is true or false, right? If I think it's false, then, that just adds some more stress to my day, and I just, try to ignore it for as long as I can. But then if people start emailing me or sending me, like, text messages like, oh, why haven't you blogged about this? Then at some point, I have to get it out of my system.
And I wait for Scott to debunk it.
So you're the one sending the email, why haven't you blogged about it? Right?
It's never been him.
I think I read yesterday, Scott said you're trying to teach the world to fish for 20 years and unsuccessfully.
But I said, fine, I'll just hand out some more fish instead.
How do you see quantum and AI? Is that just a fundraising ploy to combine them together, or is there some meat on the bone?
I think there are many, many fascinating research questions at the intersection of those two subjects. In fact, one of the first talks I ever gave as an undergrad in 1998 was about quantum computing and AI. But what I said in that talk was, I'm not really sure what speedups there are other than the Grover speedup. And I would say 26 years later, that remains a challenge. So, I think that there is no question that, classical AI will help quantum computing enormously. For example, in, enabling faster decoding of error-correcting codes or optimization of quantum circuits. There's also no question that classical AI will, to some degree, compete against quantum computing, as Demis Hassabis and others have pointed out, right? Like if you're doing protein folding or other quantum simulation problems, you now have to compete against classical deep learning being applied to the same problems. And as for how much can quantum computing help with AI, I mean, that is, for at least 15 years has been one of the great questions of quantum algorithms. But I would say, as I said in my talk this morning, it is a challenge to figure out speedups for problems relevant to AI that are more than the Grover speedup, and that are not for very specialized problems or problems that are themselves about quantum mechanics. I think that's the big challenge.
Well, the applications of classical ML to quantum hardware are happening now, and the companies and the labs are using reinforcement learning and other methods to improve performance. I'm intrigued about using classical machine learning applied to quantum problems and how far that can go. As of now, the problems that we target with quantum computing in chemistry and materials are in the strongly correlated corner of that space. for which we just don't have the training data. So I don't think we're in a position to apply AI fruitfully to those kinds of problems now. As quantum computing advances, it can provide more of that training data, and it'll be interesting to see how quantum and AI together can advance some of those problems that involve many qubit quantum systems or many body quantum systems.
A question that comes up a lot is about education of younger people. So if you have a relative, senior in high school, thinking about what to study for college, wants to go, hears about quantum computing, what would you tell him to major in?
Well, I would need to talk to this student. I would need to learn more about them and what they're excited about and what they're good at and what their goals are, right? First of all, if they wanted to do quantum computing because the word quantum sounded cool and they didn't really know any more about it than that, well then, maybe as they learn more about it, maybe their interests will change. Maybe they'll decide to do AI instead, for example. But if with eyes wide open, knowing what the subject is, they still they definitely want to do quantum computing. Then I would say are they do they think more like a computer scientist, like a physicist, maybe like a mathematician, like an electrical engineer, and based on that, maybe I could give them some useful guidance, or maybe it would just be repeating back whatever they told me.
Yeah, like Scott, I'm a bit wary of giving that kind of advice because I think the best advice is for the student to pursue whatever they feel most passionate about. And I guess I'm kind of a traditionalist when it comes to the type of education we would like our future scientists and engineers to have. I feel a little uncomfortable with the idea of tailoring curriculum to the purpose of preparing the quantum workforce. I think in quantum science and technology, as in other fields, people who are broadly educated have an advantage when it comes to making the next breakthroughs. I realize not everybody has to have the aspiration to make a breakthrough that will be potentially transformative in the field. But I think I, as an educator at a place like Caltech, feel that's the way in which I can best contribute to future science and technology.
I want to violently agree with that.
Going back to the Manhattan Project, one objection that you raised is that you're not sure that the government should be choosing which modality to focus that Manhattan Project on. So in the case of, say, Australia giving a 9-figure investment at PsiQuantum, you might have said, should we give multiple 8-figure investments to different modalities?
Well, one thing that I would say is I think that was an unwise investment by the Australian government. I suppose they know what they're doing. So you're suggesting making sizable investments to a number of different modalities. I think if that were done in a sensible way, it could really accelerate progress. And what I mean by in a sensible way is in a forward-looking way. What are the capabilities that we're going to need to make real application scale quantum devices possible in the future? It doesn't necessarily mean, taking the technology we have now and trying to scale it as fast as we can. It probably means, depending on the modality we're talking about, advances in, across the stack that haven't occurred yet. And if the government can help those things to occur faster, then that'll be good for our industry and our field.
In the last minute that we have, if you were a betting person, what do you put the probability that P equals NP?
So, well, I've already committed to this on my blog, so I guess I can't change it. I put 97% that P is not equal to NP. And Yeah.
Over 99%.
Over 99%.
That's
Yes.
equal to NP
Yes.
for me.
I'm given pause by Ryan Williams, who is maybe the most brilliant complexity theorist working right now, giving it only, I think, 75 or 80%. If not for that, I might have gone higher.
Well, Professor Aaronson, Professor Preskill, thank you so much for being with us today.
Yeah, it was fun.
Yeah. Yeah. Thanks.